Hey Phys2 kids, Campbell here. In our first video on circuits, we're going to talk about why electrons flow. Why do we get current that does things like light bulbs or run our calculators? Well, if you think about what's going on in a conductor, right, the electrons are free to move. Conductors are metals, and so there's a sea of electrons, and so the electrons are just randomly moving around, just random motion. But if we give it an electric field, so some sort of potential difference, once I have this electric field, right, I have a force, and that force drives the electrons. So once I have a potential difference, I get this electric field inside my conductor, and that electric force pushes the electrons and establishes a current in the wire. Now, what's really interesting is that these electrons are moving, right, when I get this force, but there's all these protons and neutrons inside the conductor. And so as the electrons are trying to move, they keep colliding with other charges that are in the wire. So the net result of this is that we say that the electrons acquire a drift velocity. So it's not like they're just got some smooth path through the conductor. They're bumping into things as they go. And so it's not just some straight path. In fact, I get what's called a drift velocity, and that's really the current. Now, what's really interesting is the drift speeds are actually very, very small. If we were to measure them, we'd find the electrons are only traveling at about 2.46 times 10 to the negative 6 meters per second, so teeny tiny. So to travel 1 meter, that would be 68 minutes. What? Then how is it that I flip a switch and the light goes on? Answer me that. We'll talk about that when I see you in class. Now, so we get this drift velocity established by this potential difference that creates this electric field. And so instead of talking about it in terms of drift velocity, we talk about it in terms of current. The symbol for current is I, and it's the rate of flow of charge per unit time. So equation-wise, it's the amount of charge that passes a given point in a unit of time. And the unit for current is an amp. It's a coulomb per second, but we call it an amp. We symbolize it by an A. Well, it's an ampere, named after Ampere, but we call it amps, or symbol A. Remember that current flows due to a potential difference. So if there's no driving force for the current, then those electrons are just randomly moving around. So if you think about electrons, right, electrons go towards positive charges, but when they defined the flow of current, this was before we knew what was moving and before we decided that electrons were negative charges. So the definition of conventional current is the motion of current from high potential to low potential, which is the direction of the electric field. Well, that's a problem, right? Because the only thing that moves in the direction of the electric field are positive charges, and the things that are moving are negative charges. So we know that electrons are really flowing from low potential to high potential, not from high to low. However, like I said, this was defined before we started calling electrons the negative charge, which is unfortunate. Too bad we didn't call them the positive charge, then life would be good. So we define conventional current as the flow of current from high potential to low potential, which is really the opposite direction of what's really happening in a circuit. So conventional current is defined as the motion of positive charge from the positive terminal of a battery to the negative terminal of the battery or the power source. I know, why can't we just call it what it is? But you need to know we're dealing with conventional current here in this class, which is the motion of positive charges in the direction of the electric field, which is the opposite of what's happening. I know, crazy. Now, where does this current come from? Where does this potential difference come from? Well, it's supplied by what's called an EMF, which is symbolized by a squiggly E, like an italicized capital E. An EMF actually used to be called an electromotive force, but we don't call it that anymore because it's really a potential difference, which is not a force. But we still use the EMF as the symbol for a device that provides this potential difference. So anything that provides potential difference, whether chemical, like a battery, mechanical, like wind, or the burning of coal, which causes steam to turn a turbine, which would be mechanical, or any other energy that provides this potential difference is what is called our EMF. Now, there are two types of current. The one that we're going to deal with almost exclusively in this class is direct current, which is a steady flow of current in one direction. Batteries are a great source of DC current. So electrons can only flow, the conventional current flows from the positive terminal of the battery to the negative terminal of the battery. So one directional flow. But in our houses, we use AC current, which is alternating current. And the thing that's interesting about AC current is that the current direction changes, and it's because of the way we're creating the current. And what happens, in fact, is like the electrons are sloshing back and forth. So alternating current, not a nice, smooth, direct flow, but a sloshing back and forth. And in fact, the frequency of the sloshing here in the US is 60 hertz. It's different elsewhere. So that's why, like, when you are taking a battery-powered device like a laptop and you plug it in, you always have this big thing right here. That is the conversion between the alternating current, which comes out of the plug, and the direct current, which this laptop is used to. Now, let's talk about the difference between batteries and capacitors. We talked about capacitors or parallel plates in our last unit, electrostatics, and we're going to talk a lot more about them later in this unit. And capacitors are awesome because they store charge, but the problem is they discharge them very quickly. And near the end of this unit, we're going to talk about how fast they discharge and how we can control that. But it's very quick. So like a camera flash operates off a capacitor. The blinkers in your car, the hazards in your car, anything that flashes operate off capacitors. We have capacitors actually in every electronic device. Whereas batteries are powered by chemical reactions. And so we get these reactions going on, and positive ions and negative ions are moving to different sides, and that creates this potential difference that drives the electrons or the current in my circuit. So a battery, and the rating of the battery tells you the battery's EMF. So that's the battery's voltage. And it's determined by what's in the battery. What's interesting is if we take a 9-volt battery apart, and I have some in my class, we're going to see that it's actually a bunch of 1.5-volt batteries strung together. But we'll take a look at that actually when we talk about batteries in series and parallel, or bunches of batteries in circuits, which is for another time. So we're going to work with batteries, and sometimes we're going to work with power sources that act like batteries, because there are sometimes some problems with batteries, which we will talk about later. All right, so when I see you in class, we're going to do some activities hooking up circuits and looking at how do circuits behave in different configurations. So fill out your WSQ, and I'll see you in class.